All right, everyone, good afternoon. Everyone ready for the afternoon session? Food coma, no, caffeine, all right.
Open.
The caffeine is in short supply. I have not found the coffee station. All right, everyone, so we're gonna start off the afternoon session with Lee, and we're gonna go through SMR and ZNS and some of the things you should know about the two. We have a few more talks that are very similar. So without that, go ahead.
Hey, so thank you, Jason. Start out here. I'll get those Micron guys to sit down. All right. So obviously I know a lot of you here, but for those that don't know me, I'm Lee Prewitt. I'm a principal hardware program manager in Azure CSI at Microsoft. I do a lot of work around storage standardization, storage futures, and storage evangelization on both the side for the SSD and HDDs. So, talk today is on SMR and ZNS, two sides of the same coin, and so we'll kind of start in through and trying to talk about what that means and then what that means for the software and on up through the stack. So, why are we here talking about these things, ZNS and SMR? Well, you can see the growth in both the nearline exabytes and the flash exabytes. They're both going hockey stick. And this is not even covering, as Kushagra talked about in his keynote yesterday, that isn't even going up and getting along to keep up with the actual demand that we want to do. This is just, hey, this is what's going to get built. We don't actually want to use even more than that, so we always want to press and get to the point where we use every single last bit out of every single device that we get and every single one that you guys sell. So with that, where are we talking about these stuff today? It's obviously it's acronym dense, and so I want to kind of go through just to make sure we're level setting everybody. So SMR is shingle magnetic recording. It's been around for a while now and is now adopted. We use it in our data centers today. A lot of the drive guys have been working on this for a very long time. I think I was talking with George earlier. He said he's been working on it for a decade, so that's all good stuff. ZNS is kind of a new thing, but it's a similar concept, and we're going to kind of walk through all those stages of that. But that's zone namespaces, and that's really for SSDs as opposed to hard drives. And so when you talk about SMR, there's kind of two flavors of the two different protocols on both SATA and SAS. So you have ZACT for SATA drives, and you have ZBC or zone block commands for SAS drives. And I think I actually talk about that again on the next page. So shingle magnetic recording. So this is the way that we start to figure out how to keep going on areal density on the drive. The idea that, hey, in HDD, you write on these tracks, and how do you get those tracks and going closer and closer and closer together over time so you can always get that next bump in that terabyte capacity on that drive? Well, today, it's the way the physics works. The hard drive guys can tell them about this better than I can, but the sense of the physics on this is you've got about the ability to write at a given pitch, but you can actually read at a much narrower pitch. And so if you do some tricks, and they're actually very difficult tricks, but you can start to overlap these tracks and make that areal density go up. But what that means in reverse is that up to date, hard drives have always been right in place. You can write wherever you want. You can randomly read, randomly write, get to all that data. But with this new mechanism, you actually have to write certain areas sequentially, and then you can read them randomly. And so what does that mean? So as I say here, the ZACT was kind of standardized in T13 for SATA. Zone block command standardized in T10 on the SAS stuff. We actually use both in our data centers, moving more towards SAS, but we do use both right now. The state machines for this are, as we'll walk through and look, the state machines look very similar, obviously very, very similar between ZAC and ZBC, but new standardization work being done on ZNS, we're actually trying to keep those state machines as close as possible to that ZAC ZBC model. And there's specific reasons for why we do that, and we'll talk about that later. So the idea is that you have this series of zones on these devices. Only a certain number of them can be open at a time. You're going to be writing sequentially across that zone. You're going to fill it up, and you're going to randomly read from it as you need. And as the data gets cold and we're not really accessing it anymore, you empty the zone, you basically whack everything in it, and it all goes back to 0 and you start again. And so that has certain aspects to it for both the SMR drives and for, say, a QLC device in an SSD. But at the end of the day, the whole concept here is to try and understand what the temperature of the data is, how we're writing that data, and how we can then randomly read that data back as that temperature gets colder and colder. And let's make it change. There we go. So kind of just a little quick pictorial here. And these pictorials have been around for a while for now, but you see that conventional zone concept. Here the tracks are neatly laid out. There's some area in between them, so as you ride along, you're not interfering with each other, and everything's goodness. Obviously, you end up with the shingled zone now. You've kind of squished all those tracks very close together. You're riding one kind of on top of the other as you go along on the spiral of the disk. But the read head can now come back in here and easily still get that data. But of course, if I want to rewrite this chunk, that would be bad to do it in a random condition because I'd blow away all those other tracks that are overlapping. Oh. Flipping to the other side of the coin, QLC flash. So what is QLC flash? That's quad level cell. That's the idea is that you've got 4 bits of data in each cell. You've got all these programmable voltage, so you get a whole kind of new packing density inside that device. So we went from, if you think back through the history of flash, you go from SLC to MLC, which was multi-level cell, even though it was only 2, but that's what we called it because that was the first more than 1 bit per cell. Then we started to know that we needed to kind of actually name them after the number of bits that we're putting in there. So we got TLC with 3 bits per cell, and now QLC with the 4 bits per cell or the quad. And this is kind of this along with the kind of layer stacking that all the flash guys are doing now to make these towers of bits. This is how we're keeping the SSD scaling going so that we can get more and more bits on a device. Very difficult to kind of program correctly on these things. There's a lot of work that has to be done to get the levels just right. Things happen inside the device where these levels start to shift, and you got to be able to really kind of correctly program it and then be able to process and read the bits back at very fine levels where it's like, okay, is that 10 electrons or is that 15 electrons? What is that? So, and which level does that mean? But with that process, as you have to kind of program that very exactly, it is kind of hard on the silicon inside there, the flash. And what that means is that your endurance of the bits is much lower than it would be on, say, a TLC or an MLC or back to the days when SLC drives had 100,000 programming rate cycles. So we're down to something around the order of 1,500. This is what we're kind of seeing right now. The flash guys all tell me they're going to get a little bit better over time, but maybe not very much. And so, again, this is kind of the opposite side thing is how do we treat the flash very nicely so that over time we can keep that drive going in the data center and not have to replace it every year or 2 years. So on this front, ZNS to the rescue. This is how we treat the flash as best we can to ensure that over time it's cycling at the lowest rate possible. And yeah, and Matthias is sitting there. He's Mr. ZNS, so. Right? And so as to say, we're kind of standardizing this in NVMe. We're making sure that the state machines and kind of the concepts are very, very similar to ZAC and ZBC. Only making differentiations between the 2 specs when it really means something to the media. So if it's something that's really a hard drive spinning Rust directed, maybe that can stay in ZAC and ZBC. If it's something that's really we need for some of the concepts around usage of flash and flashability, then we're going to have that in ZNS, and those will be differences that we'll need to kind of figure out how to kind of hide under the covers, hopefully. Right? So anything else? And around how the zones kind of help us with that is basically the idea of we've got very optimal write sizes, so we can write in very nice chunks to the flash, so we're not fragmenting pages and things like that. We have the ability from that to then have very optimal garbage collection, i.e. zone deletion is garbage collection, so that the drive doesn't really have to do any if we're treating it properly. And also one of the things that this does is because we're writing sequentially, as we say, and that zones are a sequential concept, then our WAF gets really close to 1, so that we know from that cycling time we can keep that flash going for a very long time. All right, and my clicker. Right, so flipping over from the hardware to the software, there's a couple of components here that we've put together in Windows to kind of make this stuff all work kind of seamlessly. What we do is we use our newer file system called ReFS. ReFS is a copy on write file system, so it's always writing sequentially. There's a very little bit of metadata that's random, but we can have ways of kind of hiding that underneath the covers. And so it's obviously very, very good for sequential workloads. Another portion that we have is what we call DAX. So that's our direct access memory driver. This is what we run to take a storage class memory like an NVDIMM or an Apache PassDIMM, how we can access that as a storage device. Now, why am I talking about persistent memory when we're talking about SSDs and NVMe? What we do is we take a chunk of persistent memory, we use these semantics on it, and we use that, where my clicker again, to take all that random stuff that we're getting from all those VMs, and so that stuff's coming in, onesie twosies, bits here, bits there. It comes in through the NIC into the storage node. Looks like, random Swiss cheese, and everybody's all, confetti salad. We can put that into the NVDIMM, look at the different heuristics of that data, and start to sequentially serialize that out to the different devices, both a ZAC ZBC device and a ZNS device. And so that's where we kind of use that NVDIMM, as I call it, a SerDes. It's a software SerDes, so it's taking all that stuff and giving us really big chunks so we can write out very nicely to these devices. So, wrapping it up, this kind of this zone concept, it's a lot of work. There's a lot of moving parts and moving components that we need to jointly as an industry work through. The device people have to kind of work through their portions of the stack and their devices, putting this together. This is not simple. The software stack has to be able to work with this as well, and that has to make changes, and then obviously some of the things like where we're consuming it, we actually have to put some other components in the system to make this work efficiently. But we're all going to do that work because at the end of the day, this saves us lots and lots of money because the devices are getting bigger and bigger still, and that's what we need. So obviously, we've been working very closely with the industry around this. We started out with SMR. SMR is actually in production in our data centers today. We're working very closely with all the folks on ZNS and the standardization in NVMe. Maybe some of you heard a little bit about Denali. Denali is kind of a concept where you talk about open compute or open channel SSD. And we've actually taken it where the Denali stuff is not quite open channel, but it's a better mix between the current protocol and an open channel protocol. And what we've done is basically, so we have the Denali standard, that's its thing, but what we do to regularize some of the use cases and to try and break this up and make it kind of consumable over time by the industry, we've taken probably 50% of the Denali concepts and the work that we did in Denali. We are now codifying that in ZNS in NVMe. And so that would kind of be the crawl, walk, run model to maybe a Denali future sometime, who knows. But we're going to get the big bang for our buck and the low-hanging fruit with ZNS right today. And so I'm going to give a shout out to Matthias for driving that within the thing. And so at the bottom, at the end of the day, the biggest thing for us is that because of the way we've architected this and the fact that these are all zone devices that work with the semantics and state machine are very similar, the whole upper portion of the stack can stay the same. And the only work that has to happen is really on that base protocol driver at the bottom of the storage stack. So with that, very quick run through. And so I wanted to do that as kind of quick as I could, and I think a lot of people already know a lot of the aspects of it. Hopefully some of the other kind of brings you up to speed on that. And then I wanted to get to the point where we could actually ask questions, because I'm sure there are questions. So, anybody have questions?
Yeah, question about the hardware. So besides all the efforts from the service stack, I'm just wondering, so from Microsoft perspective, is there any hardware limit, like vibration challenges on adopting SMR drives in your system?
A good question. So that'll be a two-part question. And in one part, I'll point to probably one of the hard drive guys to answer. But so one of the things is we design our own hardware, not obviously the commodity, the physical devices that go into this, but they're our own chassis, our own JBODs. And what we've been told by folks, which is a testament to some of the engineering done in the CSI group, I think, is that our JBOD has one of the lowest resonance and vibration characteristics across the different JBODs in the industry. So it's the worst slot is not very far off from the best slot in terms of vibration.
Okay, so you basically kind of use the same hardware for like traditional SMR drive and SMR drive?
Yep. Yep. How much?
So you're adding cost to the server with the NVDIM and additional processing on the BFS, but then obviously getting a lot of savings at the storage level. What types of savings do you expect to achieve, or could we achieve?
I would have to talk to my sourcing folks about. So frankly, I know. So it's how should I say this? I couldn't tell you a number because then I would get fired. But yeah, so you can think of it, the cost of the NVDIM and the fact that the number of person-hour development time that we put in to bring the stack up, it was well paid off for in 1 quarter by the savings that we got for the devices that we were buying. That was it.
Follow up to that, so when you say savings, are you talking about savings because you're getting the device cheaper, or savings from replacement because you won't wear out the device?
More from the fact that we continue on that scaling curve and we can get those bits in there, we can pack those bits more densely within that JBOD, within that storage node, within that rack, within the stamp, within the data center, right? So it's the idea of, hey, how do we go from a 10 terabyte drive to a 12 to a 16 to an 18 to 21? Or on the reverse, say now when we're moving forward with things like a QLC drive and the E1.L, how can we go 16 terabytes, 32 terabytes, that sort of thing. So that would be a different aspect. Not really an aspect of ZNS specifically on this one. It's more the sense of, hey, how do we, because of the underlying characteristics of the different medias, the ability to keep scaling those medias to higher and higher densities, higher and higher capacities, becomes really important for us to ensure that we have enough stuff to store all the cat pictures that people want to store.
The benefit of ZNS thinking is mainly loss reduction.
Right. Yeah. And well, yeah, and there'll be some things around OP and possibly DRAM, but it's the idea really is we're going to take advantage of all the cost savings we can, but it's the idea of how we specifically allow for higher and higher densities of this stuff because of the characteristics that are happening with it as the density scales. Oh, sorry, in front of you.
Have you seen any benefit from log-on-log, kind of right amp and over-provisioning? Because an FTL SSD is going to over-provision 30%. If you've got any kind of log structured host, it's going to be another 20%. And now you get to collapse that to 1. So your right amp is going in half, and so is your free space.
Right. So
You're saving a lot of flat.
right. So yeah, there will be aspects around that where we're going to be driving down the over-provisioning, as Mike kind of alluded to. The idea is that we actually don't do 20% over provisioning today. We actually have a much lower number, and we want to drive that down as well. Oh, and sorry, I mean, the hook is coming out to pull me off here. But obviously I can stand in the back and.
That was perfect.
Thank you.